Next one, antenna port analysis. So how to measure the S parameters of the two ports of an antenna. So that is the thing we are going to do. So here we are going to create an inverted F antenna. So there are several antenna structures available, and depending on the application you are going to use, you can use different types of antennas. Okay, so there is no on and pause rule that you have to use only this antenna for that particular application. You can use any antenna for your application as long as the parameters are optimum. See here, I'm going to create an inverted F antenna. I'm running each section. And once the antenna is created, you can see the antenna below. You can see it is an inverted F antenna. Inverted means you can see it is looking like an inverted F. See the, maybe I think if you see the top view or other view, you will be able to see it is going to look like your inverted F antenna. Okay. And I'll run once again so that you can see from the top view. If you see, you can see the inverted F structure properly. Okay, so it's an inverted F antenna. So whatever I have considered this antenna. For this antenna, we are going to measure the S parameters of the two ports. Okay. So once I design this antenna, see, I just done 2 lines of code and my antenna is ready. And this is the metal, this is the substrate, and this is the metal point where, and this is the feed point where I'm going to inject my RF signal to my antenna. And this F structure is going to radiate, giving rise to radiation pattern. Okay, so that is the structure of the antenna. Now I'm going to set the frequency of analysis. I'm going to view the response of the antenna from 1.5 gigahertz to 2 gigahertz and splitting it into equally spaced 51 points. So once I run this command, you can see the impedance plot coming. See the impedance plot at the design frequency. I can see here this is red color is the reactance and blue color is the resistance. Okay, so this is the impedance plot of the antenna. So I have taken 1.5 to 2 gigahertz range. You can choose any range what you want. Okay, so you can see that the resistance is constant, right? Almost flat. So it is constant over the entire band. So I can use this antenna for a wideband application. Okay, I can use this antenna at wideband application. The antenna is resonating at 1.74. So the point where your reactance becomes 0, that is the resonant frequency of the antenna. So this point is resonant frequency. So when reactance becomes 0, that point is the resonant frequency of the antenna. So we find that the resonant frequency is 1.74 gigahertz. And at the 1.74 gigahertz, the resistance value is close to 20. Resistance value is close to 20 ohms. But actually, the resistance value should be 50 ohms. We have seen that whatever impedance and whatever resistance you are going to match for a transmission line, everything should be done with 50 ohms. But since at the design frequency of this antenna, your resistance is only 20 ohms, so I cannot say that 100% power will be transferred from your source to your antenna. Okay. And the reactance value below the resonant frequency is negative, and the reactance value above the resonant frequency is positive, which means that below the resonant frequency, the reactance is negative, means the antenna is behaving like a capacitor, and above the resonant frequency, the reactance is positive, means the antenna is behaving like an inductor. At resonant frequency, the antenna behaves like a resistor. So RLC. So antenna is just like an RLC